There are many videos about the far future where we have full access to the limitless resources in space. There are also many videos about recent or near future technologies like reusable rockets, the Starlink network, or 3D printed habitats on Mars or Moon. But I kind of miss a discussion about the transition between those times. Hello everybody, my name is Michael Oberg. I'm a German mathematician and software developer, a fan of spaceflight and the general idea of space colonization since I was a small child. As I was about 13 years old, I stumbled upon this book, which is a German compilation of the book High Frontier by Jared Kitchen O'Neill. This book completely changed my view about space colonization, and I knew immediately that I wanted to be part of that. Now it is difficult to be part of something which does not exist, and even today there are no plans to create such a space colony. So in the last few years I concentrated on the topic of mass cargo transportation between Earth and the Moon. I have made this presentation about that, which I will show here. I will also put a download link in the description. For O'Neill, the real starting point of space industry was the creation of the first space colony. He called this concept Island 1, a space habitat for 10,000 inhabitants. In his book, he relied on a huge amount of government investments to create this first colony. That never happened, and obviously it will never happen. But in the last 2 decades, we had some remarkable progress in private industry, especially in the space launch industry. In this presentation, I will describe a way how private industry could reach the goal on its own. The presentation is split into 6 parts. The first part asks which amount of production we need to build such a space colony. The second part explains how location and transportation methods affect the costs. The third part reminds on old ideas about transportation in space besides rockets, and also explains their fatal flaws. The fourth part is a brief description of a possible transportation infrastructure from the surface of the Moon up to low Earth orbit, but under the premise that we have a cheap mass transportation system between Earth orbits. The fifth part describes exactly this solution, which I call the Skyhook Chain. This is followed by a summary. To determine the necessary amount of industry production in space, let's begin with a look at the original concept of Island 1. There are of course newer concepts, but they all have the same magnitude. The reason for that is partly the limited tolerance of humans in regard of rotation, Coriolis effects and differential gravity, and partly because of geometric reasons. If you are interested in this, the YouTube channel Cool Worlds has a good explanation in the video Artificial Gravity. I will put a link to this video in the description. Let's get into the numbers. The rotating core structure of Island 1 has a mass of about 100,000 tons. This is mainly the central sphere, which is a living area. The cylindrical structures before and after that sphere, which are agricultural areas, and the radiators for heat, for cooling the station, and the central axis, which is also used to move air between the central sphere and the radiators. Inside this body there are buildings, infrastructure like plumbing, water, soil, plants, the atmosphere, And in the agricultural area, there are also agricultural machines, which altogether builds up to about 500,000 tons. Outside the central structure are mirrors for sunlight, which are non-rotating and therefore very light, a few hundred tons at most, but also the radiation shielding. And that mass is considerable because to bring down the radiation levels inside the living area down to Earth levels, the radiation shield has to be 2 meters thick, which brings it to a mass of about 3 million tons. In order to build such a space station in an acceptable time frame, we need to boost space production to a magnitude of about 1 million tons a year. Now, on the first glance, this is not a big deal. For example, the worldwide crude steel production in 2018 exceeded 1,800 million tons, not to mention other materials. Let's make a quick breakdown of the term space production. The obvious goal is to mine resources in space, on the moon or on asteroids, and refine them and assemble them into final products in space. However, so far we never did this. Another possibility is to create products from raw material shipped into space, but this is entirely experimental. For example, in 2014, a 3D printer was installed on the ISS, which is sometimes used for creating tools. The third way is to ship ready-to-use products into space, which are mostly satellites or spacecrafts. In 2018, we had 111 successful orbital launches. However, the overall payload was definitely way below 1,000 tons. To get an idea about the growth rate of space production, let's get a look on the number of orbital launches per year all the way back to the beginning of the space age. In the 20th century, the space launch industry was mainly dependent on government investments and therefore driven by political constellations like the Cold War. With the 21st century, however, private industry became the dominant factor and created a sustainable growth. To reach the desired production rate in about 20 years, we would need a growth rate of about at least 40% a year. In fact, the growth rate was under 7% in the last 15 years, which puts the 1 million ton production goal into the 22nd century. This is exactly the reason why most space entrepreneurs are reluctant to name dates for such kind of projects. For example, a few months ago, Jeff Bezos, founder of Amazon, held a speech at Blue Origin about exactly these themes. His conclusion was,
"Who is going to do this work? Not me. These kids in the front rows, you guys are going to do this, and your children are going to do this. This is going to take a long time. This is a big vision. This generation's job, my generation's job, is to build the infrastructure so that you'll be able to. We're going to build a road to space."
How will this infrastructure look like? In my opinion, with the right components, we can build the first space colony in less than 30 years. The core of this infrastructure obviously is the refining of ores mined in space to metals at a large scale. On Earth, this requires extremely heavy machinery and human workers. It was never fully automated. It is also important that all refining processes we are using on Earth on an industrial scale rely on high-quality ores, not on soil scooped up in a random place. These ores mostly do not exist on the moon because they were formed through millions of years of submarine volcanism. In space, we have one advantage, though. We have access to nearly unlimited solar power. With that, we can indeed refine lunar regolith from a random place instead of searching for special ores. However, doing that in an Earthbound laboratory or even on the ISS does not enable us to create an industrial-scale process out of the box. Developing an industrial-scale process is always done by using and gradually modifying the industrial-scale machines itself. So obviously, we need to put heavy machinery and human workers into space to get things started. The question is, where in space? That brings us to the topic of launch costs, and at the core of this topic lies the rocket equation. Let's get a closer look using a few examples. First, the terminology. The term delta V is the velocity a rocket could reach in theory if it accelerates in a straight line without any influence of gravity or atmospheric drag. A low Earth orbit, short LEO, is a stable circular or slightly eccentric orbit of about 300 up to 2000 kilometers above sea level. Now, what is the delta V needed to reach LEO from the surface of Earth? First of all, you need to reach the orbital velocity. That's obvious. It's about 7.2 up to 7.8 kilometers per second according to the orbit. But a spacecraft has also to be lifted to the height of the orbit, that is at least 300 kilometers. Furthermore, while accelerating to the orbital velocity, it has to overcome the gravity of Earth until the gravity is compensated by the centrifugal force of its orbit. And lastly, it has to overcome atmospheric drag as long as it is moving inside the atmosphere. Overall, a delta V of about 9.2 up to 10 kilometers per second according to the orbit is needed. Now let's compare this with a round trip from LEO to the surface of the Moon and back. To reach the Moon's surface from LEO, a spacecraft has to accelerate to escape velocity from Earth, which adds about 2.8 up to 3.2 kilometers per second to the orbital velocity, according to the orbit. When reaching the Moon's orbit, the spacecraft has to accelerate to the orbit velocity of the Moon, which is around 1 kilometers per second more, then decelerate to the Moon's escape velocity while also overcoming the Moon's gravity, which adds another 2.4 kilometers per second, delta V. To come back to Earth from the Moon's surface, a rocket needs to accelerate to the Moon's escape velocity while also overcoming the Moon's gravity, around 2.4 kilometers per second, then decelerate from the Moon's orbital velocity in order to fall back to Earth, which adds another 1 kilometers per second. After this, atmospheric braking using a heat shield can do the rest. We can reach either LEO or the surface of Earth without using more rocket fuel. So for the round trip, we need another 9 up to 10 kilometers per second delta V, about the same amount as for reaching LEO from the Earth's surface. One of the most efficient rockets today is the current version of the Falcon 9, the version 1.2 Block 5. It has a takeoff mass of about 549 tons, and when it's going to LEO without reuse, without sparing rocket fuel for landing, then it has a payload capacity of about 22.8 tons, which is 4.15% of its overall takeoff mass. If the delta V needed for the round trip from LEO to the Moon equals the delta V needed for going from the Earth's surface to LEO, then you need a fully fueled Falcon 9 in low Earth orbit to do this for the same payload. In order to bring the mass of a fully fueled Falcon 9 from Earth's surface to LEO, you need more than 20 launches of the Falcon 9. So overall, a round trip from the surface of Earth to the Moon and back is more than 20 times more expensive than a visit to LEO. That cost factor can be reduced a little bit, because on the Moon you can use lower accelerations, therefore weaker structures and engines.
But the efficiency of chemical rockets is limited by the laws of physics and already near its maximum. The huge cost gap therefore stays, even if the overall launch cost can be further reduced by full reusability, which is also limited because the most expensive parts of a fucking mine already are reusable on a long-term base. From this, we can make two conclusions. First, if we can bring the lunar regolith to LEO and transport products back to the high orbits without using anything from Earth, that would lead to an enormous cost decrease. That decrease could be even larger than the difference in transport costs. In LEO, we can rely on remote-controlled robots, since with a direct radio connection from the ground station, the signal lag is below 100 milliseconds for multiple minutes. On the other hand, the lag from the ground station to the moon would be 2.5 seconds. The second conclusion is that we can't use chemical rockets at all. Remember that the round trip from the moon's surface to LEO uses at least a delta V of 9 up to 10 kilometers per second, and therefore at least 20 times as much rocket fuel as the weight of the payload. Even with possible savings by use of lower accelerations, this is at least 10 times more fuel as the weight of the payload. That means for transporting 1 million tons of products between LEO and the moon's surface, we need at least 10 million tons of rocket fuel. Even if pure water ice exists on the moon, to mine and refine 10 million tons of it to liquid hydrogen and liquid oxygen right on the surface of the moon needs a space industry which already has surpassed the 1 million ton per year production goal by far. However, there is no clear evidence for pure water ice on the moon. Until now, we only know about tiny amounts of water bound into the regolith. Indeed, the reason for the moon water hype is that most of the plans regarding it are scaled to moving not more than a few hundred tons a year, instead of 1 million tons. Rockets have not always been considered as the only road to space. Let's talk about a few alternative concepts and their flaws before we lay out the solution I recommend. The first of these concepts is the space elevator, which was first envisioned by Konstantin Tsiolkovsky in 1895. Inspired by the newly built Eiffel Tower in Paris, France, he thought about a tower built somewhere on the equator with a height of 36,000 kilometers, which puts its top on a geostationary orbit. However, there will never be a material able to withstand such pressures. Everything will eventually liquefy. But tensile strength can be much higher than compressive strength. In 1959, the Russian engineer Yuri Atsotanov envisioned the space elevator simply as a tether hanging down from a geostationary satellite all the way down to the Earth's surface. Such a structure as a whole would be even larger, 50 up to 100,000 kilometers, because a counterweight is needed above the geostationary satellite. A material used for a space elevator has to have a braking length of just below 5,000 kilometers just to support its own weight. Graphene and the so-called colossal carbon tube have shown such braking lengths under laboratory conditions, but it may take 1 or 2 generations until such a technology can be applied to a space elevator. Today, no tethered material available on industrial scale offers more than 5 up to 8% of the necessary strength. The second concept is a lunar space elevator. It differs from the Earth space elevator quite a bit. In a tidally locked system like the Earth's moon system, there are no stationary orbits around the moon. Instead, we have so-called Lagrange points, L1 and L2, with L1 located between Earth and Moon and L2 on the far side of the Moon.
and the whole system rotating around Earth like this. Now the point L1 is about 56,000 kilometers above the surface of the Moon, while L2 is about 63,000 kilometers above the surface of the Moon. So the Moon space elevator is even larger than the Earth space elevator. However, this structure needs only a braking length of below 260 kilometers, which is way below the capabilities of Dyneema, Zaldon, or special types of carbon fiber, and with a tapered design even in range of Kevlar. However, the animation does not show that the Moon's orbit is slightly elliptical, which results in movements of the Lagrange points upwards and downwards, and partly also in north-south and west-east directions due to the libration of the Moon. This is due to the fact that the Moon's axis is slightly tilted against the plane of the orbit, and the Moon is rotating at a constant speed, but its speed due to the rotation around Earth is faster when it's near Earth than it is when it's away from Earth. These movements have a range of multiple thousand kilometers. That leads to far bigger deployment and stability problems than for an Earth-bound space elevator. But the biggest challenge for this concept might be economical instead of technical. Think about a tether of about 60,000 kilometers length, which has to be absolutely flawless after its production during the whole lifetime of the space elevator, whereas the slightest flaw in this tether destroys the whole investment. The third concept is the so-called Skyhook, or also called rotovator, proposed in 1976 by Hans Moravec. A space elevator looks like a static structure viewed from the surface of the celestial object it is attached to, Earth or Moon, but in fact it is a tether rotating with the same speed as the celestial object. Examining the problem of the braking length more closely, you will notice that the stresses applied to the structure originate mainly from gravity, less from centrifugal forces. More precisely, the stresses originate from the changes of gravitation, the so-called tidal forces, not from the strength of gravitation itself. If you make the tether shorter, the tidal forces will decrease. However, in order to touch the surface of the celestial body without horizontal movement, the tether has to rotate faster, like this. The shorter the tether gets, the more the balance is shifted from gravity to centrifugal forces. However, the shorter the tether is, the higher the centrifugal acceleration will be. With a radius of 5,000 kilometers, the braking length will fall from the 5,000 kilometers needed for the space elevator down to slightly above 3,200 kilometers, and the centrifugal acceleration will be around 1.3 g. A radius of 1,000 kilometers reduces the braking length to 2,700 kilometers, but the acceleration will increase over 5.1 Gs. Obviously, with such a braking length, an Earth skyhook is nearly as out of reach as a space elevator. Perhaps even more so, as rotating out of sync with Earth causes all sorts of dynamic problems. The fourth concept obviously would be a moon skyhook, but that idea might prove to be impossible. The Moon is not as homogeneous as the Earth. Its interior was never completely molten. This makes the Moon's gravity field extremely asymmetric. As a consequence, there is no stable low orbit around the Moon. Any skyhook would crash into the ground. The fifth concept is the so-called half skyhook, which was also proposed by Hans Moravec. Other than the Skyhooks, this does not go down into the atmosphere, and its rotation does not cancel out more than half the velocity difference between Earth's surface and the center of mass of the half Skyhook, which means a shuttle would couple with the half Skyhook at a velocity of nearly 4 km per second, about Mach 13. A half Skyhook with a radius of 500 km would need a tether with a braking length of around 820 km, which is still way above nowadays materials. In addition to that, we would have all the dynamic problems of a Skyhook, the problem of producing and deploying a flawless 500 km tether, and the 4 km per second coupling with a shuttle above the atmosphere with an acceleration of nearly 3.2 g. The sixth and last concept, the Moon Linear Accelerator or Mars Driver, is the most realistic. It was first proposed by Jared Kitchen-O'Neill in 1976 in the demonstrator project Mars Driver 1. Because the Moon has no atmosphere, it is possible to use an electromagnetic coil gun to accelerate directly to escape velocity on the surface. Such an accelerator would be relatively small, only a few hundred meters long. It would shoot a steady stream of small pellets, about 1 up to 10 kg, of lunar regolith enclosed in glass or glass fiber to a collector positioned in L1 or L2. Because that concept is known since the 70s, I will not go into details yet. Just let us assume that we can assemble 1 million tons of regolith at L1 or L2 every year, but that would be only 1/4 of the problem. So, we assume that we can bring lunar regolith to L1 or L2, but first, what is needed on the surface of the Moon to achieve that? What amount of material would we have to bring to the surface of the Moon? Second, how do we bring the material from L1 or L2 down to LEO? Third and most important, how do we bring the products from the space industry back to high orbits, including L1 and L2? So, what is needed on the surface of the Moon? Sadly, I didn't find any reliable source of information about high-velocity mass drivers. Let's just assume that an installation of 1 ton is capable of shooting 1 kg pellets every minute with lunar escape velocity. About a year, that would be a mass of about 500 tons, if we can make it work also in lunar nights. For example, with a mirror in L1 or L2, or with a power station in L1 or L2 and a microwave energy transmission to the surface. Otherwise, if it doesn't work in the lunar night, it would only transport 250 tons. For moving 1 million tons of regolith, we would then need a mass driver installation of about 2,000 up to 4,000 tons on the Moon. A fleet of fully automated robot bulldozers scooping up lunar regolith and bringing it to the mass driver does barely add to that mass. Even in Earth's gravitation, a bulldozer can move several thousand times its own mass a year. Luckily, such fully automated robots are already in active development for creating both lunar and Mars-based 3D printed habitats. So we need to bring perhaps 5,000 tons down to the Moon's surface. Let's assume we do that over a period of 10 years. Let's further assume we bring the installations down to the Moon's surface using conventional rockets, but only for the transport from L1 or L2 down to the surface. For the transport from LEO to L1 or L2, we are using the technique described in the answer to the third question. The additional mass for fuel and rockets, or moonlanders, is definitely smaller than the mass for the installation itself. But let's assume everything together is over less than 10,000 tons. 1,000 tons a year is small compared with the achievements, but it is still big compared to the less than 1,000 tons overall yearly transportation of the whole world. But this number is not only an upper limit, it also does not regard any savings from using space materials. Casings, axes, gears, wiring and many other heavy parts could be made from metal gained from lunar regulus, and this is also the case for the heaviest part of the rocket fuel, the liquid oxygen. So wide savings could go up to 80 up to 90%. The second question was, how do we bring something from L1 or L2 down to LEO? As you will see, this topic is mainly covered in the next part, bringing something from LEO up to L1 or L2. But as you also will see, having an alternate path is essential. It is also essential to insert the material into an equatorial orbit. While the Moon's orbit, and therefore also the movement of L1 and L2, has an angle of 18.4 up to 28.6 degrees against the Earth's equator, changing over a period of about 18.6 years. Changing the angle of the orbital plane is possible using the Moon's gravity itself. However, there are only 2 small launch windows every month which would allow this. That is the main reason why we need the collectors in L1 and L2. Using L2 behind the Moon from the Earth's line of sight has 2 advantages over L1. First, the battery of linear accelerators, the mass drivers, can be placed on the side of the Moon visible from Earth, which allows direct contact with the Moon base. Second, a payload launched from L2 can use gravity assist by the Moon for a flight to Earth. Reaching LEO can eventually be done with successive atmospheric braking maneuvers during multiple elliptic orbits, each with a lower apogee than its predecessor. The third question was, how do we bring payloads from LEO to high orbits, including L1 and L2, without using rockets? That's exactly the culprit here, the key component of the whole concept. Finally, let's go beyond skyhooks. There are 2 causes for stress in a skyhook: gravitational, more precisely tidal, force and centrifugal force. Tidal forces are only relevant for structures of multiple 100 km size, so downscaling the skyhooks removes this issue completely. The necessary braking length of a rotating tether not affected by tidal forces is proportional to the velocity squared of the tether's ends. So, if we split a skyhook into 10 parts, each part creating only a tenth of the overall velocity difference, the necessary braking length for each part goes down by a factor of 100. Furthermore, the centrifugal force is proportional to the rotation velocity squared divided by the radius. Therefore, if the velocity is reduced by a factor of 10, it is possible to reduce the tether's length by a factor of 100 without changing the centrifugal force. If we only try to overcome the velocity difference between LEO and high orbits, basically the escape velocity, instead of lifting payloads from the Earth's surface into space, this leads to further reduction. We end up with rather strange-looking asymmetric vehicles. A 2-kilometer-long tether with a heavy payload attached to one end and a lightweight gripper to the other end. Obviously, it only makes sense to cut a skyhook into pieces if these pieces can periodically recombine and successively accelerate the payloads into higher and higher orbits. That creates not only engineering challenges, but also one for orbit mechanics. The basic idea is 2 spacecrafts catch each other with the grippers on the tether ends, swing around each other 180 degrees, and release each other again. This would completely exchange their impulses. On the image below, the red spacecraft would continue to fly on the original course of the green spacecraft and vice versa. In a pure Newtonian environment, in an environment where orbits are only defined by Kepler's laws, it is easy to find a suitable orbit configuration. Below is an example of 11 orbits starting with a circular orbit 437 kilometers above sea level. The velocity in perigee goes up from 7.6 kilometers per second to 10.5 kilometers per second, but on every step the acceleration is below 300 meters per second. Also, the difference between the perigee velocity on the 11th orbit and the escape velocity of about 10.8 kilometers per second is below 300 meters per second. The last two columns show how often spacecrafts on two successive orbits would rejoin. The longest time is between the second and the third orbit with 6.5 days, which suggests we can lift 55 payloads every year. This configuration has to be changed slightly because of the duration of the impulse exchange. In fact, the spacecrafts join together before reaching the perigee of their respective orbits. When joined, they are flying on an orbit which is not identical to any of the original spacecraft's orbits. This means that the perigees of consecutive orbits differ by a few kilometers. And even more important, it also changes the timing by a few seconds, by accelerating the slower and decelerating the faster spacecraft during the joint rotation, which is, by the way, a little bit more than 180 degrees. The change of the perigee doesn't affect the orbit's period as long as the apogee is changed exactly the same amount. The time change per exchange is mainly compensated by the fact that there are as many exchanges upward as there are exchanges downward. So now the system should look like this. But instead the orbits look like this. As you can see in this animation, the orbit's major axes are slowly rotating in the same direction as the spacecrafts are rotating around the Earth. The reason for this is that the gravitational field of Earth is not spherically symmetric. Since Earth is rotating, its equatorial diameter is larger than the polar diameter, 12,756 km equatorial instead of 12,714 km polar. This affects orbits near Earth more than the Moon, the Sun, or anything else. For example, on a non-equatorial orbit, this leads to a rotation of the orbit's plane, so-called precession. This effect is put in use for Sun-synchronous or Molnier orbits, for example. For the Skyhook orbit system, rotating orbit planes would be devastating, because the planes would rotate with different speeds according to different apogees. That is the reason why all Skyhook orbits have to be equatorial. But that alone is not enough. Even inside the equatorial plane, the gravitational field is distorted. Not in direction, but in strength. The field is stronger than compared with a spherical planet, but only near the surface. The further away from Earth, the weaker the field distortion is. This results in a slow rotation of the semi-major axis of any elliptical orbit. Per orbit cycle, the effect is stronger the higher the apogee is, clearly visible in the outermost orbit. But because the smaller orbits are cycling much faster, the semi-major axes have a faster rotation. But here's the trick. The same effect applies to a non-spherical spacecraft. The only reason this was never taken into account is that no spacecraft ever built was large enough to have a measurable effect of that kind. Two heavy weights connected to each other using a multiple kilometer long tether is a different thing. And by rejecting the tether, the effect can be precisely controlled. The idea behind this is not to stop the rotation of the semi-major axis, but to accelerate it in the outer orbits, so that all semi-major axes stay aligned. Using Dyneema as tether material could enable the spacecrafts to carry 100 times its own weight as a payload if a highly asymmetric design is used. With a symmetric design, which maximizes the gravity distortion, it is still capable of carrying 50 times its own weight. With 55 flights a year, this results in a system capable of moving several hundred times its own mass every year. This is at least as lightweight as the Lunar Linear Accelerator system. Still, it should not be concealed that mining the Moon will not provide us with cheap space dynamo or a similar material. Good sources of carbon and hydrogen will be found in the asteroid belt, but the mini Skyhook chain described here will not give us direct access to that. So, what I am proposing for kickstarting the space industry is building an extremely lightweight transport infrastructure which gives us access to millions of tons of moon materials in low Earth orbit and also the possibility to lift products generated from it back to high orbits. This infrastructure consists of a fleet of autonomous robots to accumulate regolith on the moon's surface, a battery of linear accelerators, coil guns or mass drivers, to shoot a steady stream of regolith pellets to L2, a mass collector in L2, a launch mechanism in L2, probably also a rotating tether, to inject payloads into Earth orbits using gravity assist twice a month, a fleet of Skyhook-like spacecrafts in a pattern of elliptical orbits, exchanging impulse with each other, distribute the same amount of mass upwards and downwards. An alternative flight path would include successive atmospheric braking. This allows to transport more mass down to LEO than back to high orbits, which is important due to the fact that production will never be 100% efficient. But there are two even more important facts related to building this transport infrastructure. It can be scaled down to an easily installed demonstrator project, only capable of lifting 1 ton or even less at a time. It basically uses moon dust, regolith, as rocket fuel, so even the very first demonstrator installation can be used to lift cargo up to the moon and L1 or L2. The second point is very important for investors. For example, in 2016, the United Launch Alliance announced the Cislunar 1000 vision, in which they offered to pay $3,000 US for 1 kilogram of hydrolox fuel delivered to LEO to drive their space-like ACES, Advanced Cryogenic Evolved Stage. But 1 kilogram of lunar regolith inside the Skyhook chain can produce more transport capacity than 1 kilogram of hydrolox, even without any refining. Another important information is about SpaceX's Mars colonization program. According to the latest news, Starship will not only be capable of transporting multiple million tons of material from the Earth's surface to LEO every year, but it is also required to do that for the Mars colonization program. But this mass again consists mainly of rocket fuel. In case of Starship, it is not hydrolox, but methalox. However, methalox consists of nearly 80% liquid oxygen, which could be produced from lunar regolith. The fueling process could also be relocated from LEO to a high orbit, which reduces the overall fuel consumption. And it might be possible to create some of the material needed for the Mars colony from lunar regolith, reducing the overall mass to be launched into orbit. Altogether, the costs for the Mars colony could be reduced by 80% or more. It might even be accelerate the Mars colonization program because the number of required launches is also reduced by 80%. Repeating the question from the beginning, the following answer seems viable. Developing this Skyhook chain technology may last a decade. Then a first minimal installation assembling lunar regolith, bring it to LEO and transport material back to high orbits could be working. Growing this small system into the 1 million ton per year size may last a second decade. Using this to create a heavy space industry capable of building space colonies like Island 1 should then take less than a third decade. So, what do you think? Is a Skyhook chain, like said for TED Talks, an idea worth spreading? Please leave your thoughts and questions in the comment section. Share the video with everybody who you think might be interested. Hitting the like button will also help distribution. Also, feel encouraged to make your own videos with summaries of this long explanation. I will probably go in the opposite direction and provide even more details and explanations of system parts in future videos. Let me thank you for staying with me through this long presentation. Hope to see you again and have a nice day.